Great. So let's get started here. Thank you. So this is a session on the Amazon on AWS track. In this particular track, we feature solutions that were built by teams across Amazon. This particular talk, the solution was built by Amazon Ads. As you see, Amazon is a group of more than 100 different entities. You may know some of them: Prime Video, Ads, Ring. But common to all of them is the scale at which they operate. As this slide builds up, you'll see some rather large numbers, whether it's storage, whether it's throughput, or in general capacity. These numbers are really huge. And a fun fact over here, these numbers that you see on the screen is not for a duration of a year. It's not even for a duration of a month. It is for a duration of 4 days that happened in July. The Prime Day event that happened earlier this year, these are the stats for that event. Let's do a quick show of hands. How many over here have used consumer LLMs such as GPT or Gemini? Before I could finish the sentence, I saw people raising their hands, so that's a good thing. Great. So if you use LLMs, you know that when you're using LLMs in a process that is deterministic, it is challenging, right? And at Amazon scale, that adds layers of complexity to that particular challenge. Well, if you wanted to know how you can go about solutioning this is the session for you, right? And I'm seeing all orange headsets. That's a good thing. You're listening to my session and not some other session there. So that's great. Okay, so in this session, you'll learn how Amazon Ads harness the power of LLMs to understand their shoppers in more deeply. And this understanding helps them deliver better outcomes for their advertisers. You'll also learn the architecture that they use to build this solution. This architecture was built on AWS. All the fine-tunings, all the optimizations that they did, we'll share those with you. So I'm Varun Kamalakaran. I'm a Principal Customer Solutions Manager at AWS. And joining me are Shenghua Bao, who's the Director of Sponsored Advertising from Amazon Ads, and Bolay Chen, who's the Senior Manager in Shenghua's team. He was tasked with building the solution. So our agenda for today. I'll go through the introduction. I'll talk to you about the relationship between Ads and Amazon, how this whole engagement got started. I'll pass it over to Shenghua. He will talk to you the use cases they pursued. Also, he'll set context to why a Gen AI-based solution was the right option for them. Then we'll have Bola on stage. He'll walk you through the journey about building the solution, what fine-tunings he did, what architecture options they chose, and he'll wrap this up with lessons learned. So let's get started here. Amazon Ads, on one hand, is a customer of AWS, just like you. They use AWS services solutions to build their own products, their own services, and give that to their customers. On the other hand, they're a partner. We package our products with theirs and provide that to our joint customers. So this dual relationship has been greatly beneficial to us. Now, to look a little bit about where Ads came from. As you imagine, they were born in the cloud. Their first product, which was more than a decade ago, was Amazon advertising product. And as their customer base has grown, and as more and more people have joined their platform, they've built more complex products. They were an early investor in AI, and most recently, they've launched 2 products, Creative Agent as well as Ads Agent. They're both agentic solutions built on AWS. A look into the services they use. Early on, as you'd imagine, they started off with EC2 with S3, foundational building block services, and they moved on to have more complex, more managed services, orchestrated services such as step functions or EMR. They were the early adopters of SageMaker AI, and most recently, Bedrock. But the key stat here, They use a vast majority of AWS services. They use more than 180 different services. And for each of these services, they push us. They help mature the services. They tell us, hey, this feature is not there. This capability is missing. Hey, can you do this for us? So we take the feedback, we build those capabilities, we mature the service, and that benefits our customers, such as you. So in general, our partnership has been mutual, has been fostering. And to give you a little bit more context into the use case, I'm going to bring Shenghua on stage. Shenghua, please take it over.
All right. Thank you, Varun, for the introduction. It has indeed been a great journey with AWS together. Next, I'm going to introduce a little more about Amazon Ads, how it works, and the new opportunity Gen AI introduces. Nearly 20 years ago, Amazon asked a simple question. How can we combine great shopping experience with brand discovery through advertising? Today, hundreds of millions of shoppers engage with Amazon through different channels. They can stream a video, they can shop at Amazon, or interact with Alexa. Through these interactions, we learn how Amazon shopper discover product, explore brand, or make purchase decisions. With this in mind, we use this learning applied to the full funnel advertising solutions to help advertisers to reach customers at scale. Let's make it more concrete using one example in the Amazon store. This is a query for Halloween costumes. And this is one of the favorite queries for the seasonal query I have. When a shopper searches for Halloween costumes, they may start with seeing a particular brand recommendation, along with a featured product to build the brand awareness. As the shopper continues browsing, we may surface more relevant product in the search result for consideration. Or product groups share a certain attribute to help the shopper with navigations. When the shopper clicks the product and lands on a particular page, we may also surface the complementary product or alternatives to support the purchase decision. So with that, what's behind the scene is how it works. Given a query of Halloween costumes, the Amazon Ad Search system needs to first retrieve the most relevant subset of product from hundreds of millions of ASINs. This is oftentimes in the order of tens of thousands. We then use machine learning models to score these candidates and reduce to a few hundred. And then we finally select a few to present to the shoppers. On a daily basis, we need to process billions of such requests. And this experience is empowered by hundreds of models behind the scene running in real time. Now let's zoom in a little bit even further to the models, how it typically looks like and how it matches an ad to a particular shopper. The model oftentimes takes multiple inputs, including the queries, the search context, including the product features of the candidate ad. It can also include the shopper signals. With all of these inputs, the signal flow into a neural network architecture, which oftentimes include attention mechanism or mixture of expert designs, and eventually produce a probability score, which can tell how likely a shopper is going to click or purchase a particular product item. Without going into the technical details, this model oftentimes have billions of parameters, and during inferencing, we need to perform tens of billions of operations within a tight latency budget for 40 milliseconds. These models are useful and effective in predicting the likelihood. However, these models are not good at telling why a particular product is a good match and why it is not. That's where Gen AI can make a difference. These are some examples we saw earlier. Imagine now we as advertisers. We might ask a question, given this product, who are the shoppers that might be interested in these items? Gen AI can take the model, product, and also image, title, description as input, and produce who are the shoppers likely interested in these items. They can be either looking for fantasy scenes or traditional costumes, as well as simply for fun options. Similarly, Gen AI can help with shop understanding. Imagine we have two shoppers looking for the same query of Halloween costumes. Even though they start with the same query, their behavior may tell they are having different interests. And the Gen AI is good at telling the nuanced difference as a shopper engages with a different product. In this case, Gen AI can tell, for example, John might be looking for some fun, attention-grabbing looks, maybe for a special school event, while Alice may be looking for some fantasy scenes with elegant design. Now with both product understanding and the shop understanding in place, Gen AI can also further help reason about the matching. We know the taste John and Alice is looking for already, and the Gen AI can help identify the fourth group as a potential match for John and the first group as a potential match for Alice, with the rest of the product further explaining why they are not as good match, or with human understandable languages. From these examples, we can tell where Gen AI model is good at. It understood the machine learning and also understood the human language. It possessed the word knowledge, able to tell the nuanced difference of the product attribute difference. It can also understand the evolving shopper interest. With that, it can also understand and reason about why a particular product is good or not a good match for a particular shopper. These are all promising directions we are exploring, but it comes with challenges. In particular, the Gen AI model can go up to tens, hundreds of billions. And many of the use cases require us to respond within sub-second. In particular, we also need to respond to the evolving shopper interest and campaign changes. All of them need to respond to the requested scale of billions a day. With many use cases of LLM in place, this workload can translate to something that is 10x bigger than the common consumer language model we are using today. With that, I'm going to introduce Bola to the stage to talk about how we built the solution and the lessons we have learned so far. Bola. Oh, sorry. Thank you.
Thanks, Ren and Shenghua, for the great setup. In the remaining of the session, I will mainly take you behind the scene of how we build a dedicated LLM inference service to support the Gen use case you just heard about. Let's recap on the main factors that can shape LLM inference performance. The first idea coming to mind is model size. In general, bigger model means more compute and higher latency. That is straightforward. Second, token length. Longer input token as well as generated output token, they both add additional more work per request. And together, this affect latency and throughput each single host can deliver. But these two are just half the story. Latency SLA, as well as overall traffic volume, also affect how much capacity your system actually need. And here's a universal rule. Latency and throughput, they trade off against each other. That being said, if you need super low latency, of course you will need more capacity, which means more cost. With this idea in mind, let's revisit the Gen use cases and see how each one puts this factor in different ways. Let's go back to the product understanding example, the one which we try to figure out which shopper segment would love different type of Thanksgiving costumes. Historically, we rely on product image, title, and brand embedding to represent the product. This works, but not very well when the goal is to identify difference and nuanced shopping intent, like shopper who may like attention-grabbing looks. While LLM can unlock a richer view by digesting full product description, customer reviews, as well as other long-form content, which can easily go up to 100,000 tokens. Because these information are relatively static, we don't need super low latency here. What matters is high throughput, as we need to generate hundreds of millions of requests on a daily or weekly basis. On the infra side, we use AWS step function and event bridge to orchestrate these large-scale offline batch runs. Data flow from S3 into a throughput-optimized LLM endpoint, which is capable of high concurrency. Then we sync the data into a storage layer on Elastic Cache and S3, where other ads ecosystem will consume as additional signal. Let's move to the shopper understanding example. Here, the goal is to infer what actually a shopper is looking for based on recent activities. For example, from a few clicks, LLM can tell John is a shopper who prefers fun and humorous product. To do this, we assemble a session context, consuming raw signals like clicks, items viewed but not click, purchase, and even product in a shopping cart, and putting them into an input prompt. Then LLM can reason about why a shopper might like or dislike a product. And typically, this input prompt range from a few hundred to a few thousand tokens. Latency-wise, we aim for what matters, as long as it can return before shopper's next engagement with Amazon, which is typically a few seconds. We don't need to optimize for the minimum value to balance cost and efficiency and throughput. On the infra side, we leverage Amazon-managed Kafka and Flink to scale our streaming pipeline, which is capable of handling hundreds of thousands of QPS. Within the streaming pipeline, it makes asynchronous call to LLM endpoint. And similar to offline batch inference, LLM output are written into a storage layer. We have covered offline batch inference and near real-time inference. There are also scenarios where real-time decision-making is critical, such as shopper product matching, as well as use LLM to assist with product ranking. Here, latency is the most important thing, because we need to return response within a few hundred milliseconds, while supporting a scale of hundreds of thousands QPS. To do this, our ad server make direct synchronous call to a latency-optimized LLM endpoint, right within it ad server workflow from different components, including ad sourcing and ranking. Now that we have covered several GenAI use cases, let's summarize on the key tenets and what do they mean to our system requirement. First, we need the flexibility across many aspects, including model selection, workloads, optimization objectives. The system needs to support diverse use cases as model and application continue to evolve. And second, we need high throughput whenever possible for cost efficiency, especially for heavy load from offline batch inference and near real-time inference. And finally, for certain scenarios, we do need ultra-low latency so that LLM inference does not introduce additional delay to existing shopping experience. With this tenet in mind, we developed a dedicated LLM inference solution using a hybrid stack of both software and hardware. The service runs entirely on Amazon Elastic Kubernetes service with a mixture of EC2 instances to support different demands. This choice is not only for cost efficiency purpose, it actually also helps us navigate through GPU constraints. Actually, many of our workload can run on more readily available instance types such as G6E, rather than competing high-demand instances such as P5 or P6 with NVIDIA Blackwell GPU. At the orchestration layer, we develop a model router and the job scheduler. This module help route traffic to the right model and schedule offline batch inference jobs based on their priority and current capacity status. For software, because this space evolves so fast, and different model servers, including VLM, TRT-LM, and SGLong, they can offer different optimizations. We try to keep our technical choice and the system flexible enough. We auto-benchmark different configurations, compare their performance, and pick the best setup for each use case. And finally, system optimization is very critical, talking about running LLM in production at scale. we integrate with NVIDIA Dynamo to adopt several of the promising optimizations, which I will cover in a moment. Let's also talk about how holistically this system integrates with other at its ecosystem. It provides a lightweight Java client for ad server to make direct synchronous call for real-time inference. It also allows streaming pipeline to invoke for near real-time inference. Shopper streaming event, including view, click, add to cart, purchase. When this signal flow into a Kafka and Flink managed streaming pipeline, it makes asynchronous call to the LLM endpoint using the same Java client. And for large-scale offline batch inference, we offer a batch interface for different teams to submit and schedule their jobs. Aside from real-time inference, where ad server make a direct call to the LLM endpoint, for both offline batch inference and near real-time inference, they follow the same pattern by writing LLM output to a storage layer managed by Elastic Cache and S3, where ad server will consume them as additional signal. In the next few slides, I will walk you through several optimizations we found effective to our application use cases for your reference. Let me set up some context first. In LLM inference, the first output token depends on the entire input prompt. And after that, model generates output tokens one at a time in an autoregressive loop. The phase with precise entire input token is called prefill, and the subsequent token-by-token generation is called decode. In addition, to better leverage GPU, modern model servers normally adopt continuous batching, which pack requests of different sets together, mixing prefill and the decode stage within the same batch at the token level. Because prefill and decode can run within the same batch, latency is always gated by the slowest phase, and typically it's prefill. And as you have large model or longer input token, this is even more visible as latency penalty to prefill stage is bigger. As you can see in the example, assuming we have 4 requests in a batch, when request 5 arrive with its heavy prefill stage, it can cause interruption to the decode stage of other requests. And of course, it delays the other requests. To deal with this inefficiency, one idea is called disaggregated inference, which separates prefill and decode stage onto different containers and services, allowing them to run and scale independently. This can lead to better utilization of your resource and improve both latency and throughput. Still remember the near real-time inference shopper understanding example, where our input token ranging from 2,000 to 4,000 tokens is much longer than the output token size, which is only 200. Here, the prefill interruption is unavoidable, but that is why the optimization can be effective. For example, we configured a disaggregated setup using NVIDIA Dynamo with a setup of 12 prefill workers, each with 1 GPU, and another decode worker with 4 GPU. Testing against the QN235B model, you can see this setup achieved up to 50% of the throughput optimization under same latency SLA as compared to the aggregated setup. Another powerful idea is called the KV-aware routing. Still, a little bit of context first. KV cache is a technique used to improve inference performance by storing intermediate result and computation from previously processed tokens. As you recall, a token can be represented as a vector of floating point array, also known as embedding. And for your simplification, you can imagine KVQ or the key value query. These are matrices that being used to compute the internode interaction score from these embeddings. While multiple requests they share overlapping prefix, KV caching can help avoid redundant computation. KV-aware routing takes this one step further by directing requests to the GPU worker, which already holds the most relevant cache data. In this example on the right, you can tell requests from same user almost share same input prompt, except the last moving part, which is shopping query. Well, when we a direct request from same user to the same GPU worker, this can maximize KV cache hit rate and help avoid unnecessary computation. Again, in this benchmark running on NVIDIA Dynamo against the 32-bit model, you can see with KV router enabled, this setup help reduce latency, end-to-end latency by 20 to 40% at different percentile. And the difference is even more obvious if we focus on the prefill stage or the time to first token alone. Now let's take a look at the key enablers for this optimization. At the data plan layer, we use Amazon EKS to orchestrate and manage a cluster of over 10,000 GPU of different instance type. This is the foundation for us to build a scalable service and also adopt some of the optimizations. For high-performing networking, we use AWS EFA to accelerate inter-node communication, as well to better leverage network bandwidth. This is also essential for us to run distributed inference and adopt some of the optimizations. And finally, we integrate with NVIDIA Dynamo, which bring together several key system-level optimizations, including KV router, disaggregated inference, as well as low-latency data transfer. Together, these enabled optimizations and help with our latency and throughput. Here's another thing we'd like to cover. So we all know GPU are expensive, right? And sometimes you might also face GPU supply chain constraints. Of course, you don't want to waste your money or hardware. So do we. Beyond system optimization, another practical idea is to increase your resource utilization is to dynamically allocate your capacity across different workloads based on their traffic pattern. Fortunately, real-time inference for shopping sites like Amazon has a pretty predictable daily traffic pattern. As you can see, there is clear daily traffic peak and the valley in the chart. Real-time inference must meet this demand. However, offline batch inference load, they do not need to compete for capacity during this peak hour. That being said, before traffic peak hour, we can allocate more GPU to real-time inference service to meet the latency SLA. Well, as we enter into the offline off-peak hour, the same GPU can be shifted to support offline batch inference workload. So overall, we do not over-provision on capacity. Another important aspect of running GPU at scale is dealing with hardware fault. Typically, GPU has a lifespan from 3 to 7 years, and over time it becomes malformed, showing symptoms like higher latency or even exception error code from your response. For a cluster running over 10,000 GPU, this issue can actually happen on a daily basis. So we leverage AWS CloudWatch to continuously monitor this signal. And we mark a GPU instance for replacements whenever we identify degradation on some of the signal. This helps with our system's availability without human intervention from our engineering team. Okay, so this almost concludes the main topic we'd like to cover. Our journey is still ongoing, but we still want to share some early learning with you. First of all, as you can see, we did not build everything from scratch. Actually, we heavily rely on a big range of AWS services and offerings. This is the key for us to achieve the scalability and the reliability we need, and also free us to really focus on building the application layer, business logic, and try different optimization ideas. Second, we stay close connected to industry partner and the community. This is very important for us to adopt optimizations and new solutions even earlier than their GA. We always keep in mind to keep our system flexible and open. So whenever we adopt new approach, new capability, we do not need to re-engineering the entire stack. And finally, not every emerging new optimization work for your use case and application out of the box. It's equally important for you to work closely with your application partner to understand their use case, including their traffic pattern, their input prompt design, their optimization objective. This information can help you make right decision for solution and for optimizations. Finally, we'd like to acknowledge AWS teams as well as NVIDIA teams, including NVIDIA AWS and NVIDIA Dynamo team, to their partnership. Actually, their support spanning from optimization benchmark to helping us adopt Dynamo running on Kubernetes, on EKS. This is instrumental for us to bring the technical solution into production at scale. Thank you everyone for your time, and I'm handing over to Arun.
Thank you, Bola. So as Bola mentioned, you saw the solution approach was rather simple. It was built on foundational building blocks, right? You can use the same approach, the techniques that Bola mentioned, in your use case. That concludes our session today, but before I let you go, please visit the Amazon demo in One Amazon Lane. It is located here in Caesars Forum. If you scan the QR code there, it'll tell you the location, where it is. This is a curated list of demos. If you were wanting to know what our delivery drivers use from a technology perspective, what's in the Rivian van, there is a Rivian van there where you can go check it out. If you wanted to know what Prime Video is doing for their live sports, what X-ray means, there's a demo for that. And also, finally, there's the Zoox Robotaxi. It's a cool piece of technology. If you've taken a ride in Zoox, you'll know what I'm talking about. If you haven't, go check that out. So that's all in the One Amazon Lane, right around the corner here. That concludes our session. Thank you very much for joining us. Please do provide us feedback. Go to your app, let us know how we did. And if you're able to, if you're having any agenda, any sessions that you'd like us to have in the next reInvent, put that in there. Thank you very much. You have a wonderful rest of the day and reInvent. Thank you guys. Take care.